My name is Benjamin Kiefer, and I'm going to present the work SeaDronesSee, a maritime benchmark for detecting humans in open water. As the title suggests, in this work we consider unmanned aerial vehicles and their use in search and rescue scenarios. UAVs become increasingly important in maritime search and rescue missions as they are highly flexible, comparably cheap, and fast to operate. They can be used to search large areas for people and boats at distress. We note that in this work we do not focus on path planning or communication, but instead on perception with its subtasks of object detection, single object tracking, and multi-object tracking. However, there's a lack of large-scale datasets in maritime environments. Most of the available UAV-based datasets are captured on land, often focusing on traffic environments such as VisDrone and UAVDT. The datasets that are captured in maritime environments fall in the category of remote sensing. However, there's no dataset focusing on UAV-based maritime human detection. This is where SeaDronesSee comes into play. We collected and annotated a large-scale RGB dataset in this domain, annotating over 400,000 instances, trying to introduce as much variation as possible. Now, perception from UAVs in maritime environments is particularly difficult because of reflective regions on the water and very small objects, because typically large areas need to be searched quickly. For example, look on the right-hand side where you can't see the people that are present. Moreover, people may be occluded by waves or sea foam. SeaDronesSee is the first dataset addressing these issues and tries to bring deep learning to search and rescue. Note that the mentioned challenges are on top of the general UAV-related challenges. A further advantage of SeaDronesSee is the availability of metadata. As shown in the fast-forwarded video, each frame is annotated with precise metadata information such as altitude, angle of view, time, and others. We believe that multimodal models that incorporate these information will outperform metadata agnostic models. After all, these informations are very indicative of relevant factors such as size or appearance. We collected the dataset using consumer-based and professional UAVs with 5 different cameras, of which some are video cameras. Using these UAVs, we traversed an approximately 2 by 2 kilometer large sea area on multiple days with different weather conditions. We asked 20 subjects to swim and float, hereby trying to introduce as much variation as possible, changing factors such as UAV altitude, viewing angle, clothing and life jacket colors and types. Subsequently, we hired a set of annotators to annotate the objects of interest, which are swimmers, floaters, and others. With the annotated footage, we propose 3 tasks. The first is object detection with over 5,000 images. On top of the previously mentioned challenges, this task is hard since there are imbalances with respect to camera type, category ID, altitude, and viewing angle. The second task is single object tracking. Note that we do not support long-term tracking and only provide tracking clips for swimmers, floaters, and boats. The last task is multi-object tracking, where we introduce 2 subtasks: multi-object tracking swimmer, where only swimmers and floaters need to be tracked, and multi-object tracking all objects in water, where also boats need to be tracked. We provide initial baselines for each of the tasks. For object detection, we train various models from very large 2-stage detectors to 1-stage detectors capable of running in real time. The provided metadata allows us to analyze the model's performances on certain domains. For example, we can split the viewing angles into 5 intervals, where R would be 90 degrees facing downwards and A would be horizontally facing. Remarkably, there is no easy domain in that every object detector performs best. The metadata helps show the weaknesses of individual models that could be addressed subsequently. We also provide baselines for single object tracking and multi-object tracking, which you can see in our paper. To quickly demonstrate the usefulness of metadata on a model's performance, we compare a traditional faster RCNN with ResNet 50 backbone to a so-called expert model that incorporates the altitude and the angle information respectively. Using the metadata, we can improve the accuracy across all domains individually and overall. Finally, I want to introduce to you our evaluation webpage. We withhold the annotations for the test sets and build a web server where researchers can upload their predictions to be fairly shown on a central leaderboard. Make sure to check out the webpage in case you are interested in evaluating your model.
Thank you very much for your attention.